Here we are looking at example 6 from our 1.5 number 2 set of notes. We're asked to evaluate the following limit. Now, if you were to try using that direct evaluation, you would end up with an infinity over infinity indeterminate form, and unfortunately that's just not going to quite work out. So as a result, there has to be something algebraic that we can end up doing. What I'm going to go ahead and do first, though, is apply our limit to every single item in here, much like we did with example 5. So then we end up with the limit as x goes to infinity of x squared plus the limit as x goes to infinity of 2x, and this is over the limit as x goes to infinity of 3x cubed minus the limit as x goes to infinity of this 4x squared. Now, you could divide the entire top by x squared. Again, we're looking at the degrees of these, and here they are. The highest degree on top is this x squared. The highest degree on the bottom is this x cubed. And you could divide this by x squared. However, what we're going to do is divide this instead by x cubed on top and bottom. And the reason for that is even if we divide this bottom by x cubed, we will end up with a constant as a result of that. And as a result, you can end up then with the bottom having at least a number there. And that's okay. As long as the bottom has a number, we're okay and it's not 0. So we're going to divide the top by x cubed, and likewise we're going to divide the bottom by x cubed. So once we do that, we end up then with the limit as x goes to infinity of this x squared over x cubed plus the limit as x goes to infinity of 2x divided by x cubed. On the bottom, we have the limit as x goes to infinity of 3x cubed over x cubed minus the limit as x goes to infinity of 4x squared over x cubed. So again, pretty much we're just dividing every single term by x cubed. And again, the reason why we can do that is because this is really a fancy form of 1 right here. We're dividing the top by x cubed, we're also dividing the bottom by x cubed. That's the exact same thing as saying we're going to multiply the top by 1 over x cubed and the bottom by 1 over x cubed. So as you can see, this is just a really fancy way of saying 1. Alright, so that's why we can do this. Now, just simplifying some things, we end up with the limit as x goes to infinity. There's x squared and x cubed on top, so we'd end up with 1x on the bottom still, plus the limit as x goes to infinity. Because we have a 2x on top and x cubed on the bottom, we'll have like an x squared on the bottom, and those cancel out, so we'd end up with 2 over x squared. On the bottom, we have the limit as x goes to infinity of this x cubed divided by the x cubed. Those will just end up dropping out, leaving us with that constant 3. And again, that's really what we were hoping for, where we'd end up with that constant. The limit as x goes to infinity. This x squared will cancel out with this x cubed, giving us with just the 1 left over. So we end up with 4 over x. Now, when we think about these a little bit more conceptually with our limits, if you were to throw in infinity into this, you'd end up with 1 over infinity, and that's going to be pretty small. In fact, that's going to be pretty much approaching that limit of 0. For this guy, it's pretty much the same thing. You have 2 over something that's really large. Squared makes it even larger. So something really small over something really large is going to approach 0 as well. Now the limit as x goes to infinity of this number 3 is just going to remain 3. Same thing is going to happen with this limit, where it's approaching infinity. You'd have 4 over something really large. That's going to approach that limit of 0. So as a result, we end up with 0 plus 0, that's just 0. On the bottom we have 3 minus 0, that's just 3. But notice, we end up with numbers, especially on the bottom, like we don't have a 0 on the bottom, that undefined statement. Likewise, 0 divided by any number just comes out to be 0. So this limit should be approaching 0. Now, you could have divided the top and bottom both by x squared. You would have come up with 3 x cubed divided by x squared. That would have given you 3x on the bottom, so instead you would have had this on the bottom. But you would have at least had some number. So you would have maybe had, like, I think it would have been 1 on top over 3x on the bottom. And you still would have applied that limit, so you would have ended up then with 1 over something getting really, really large. And that's the same idea as it's going to 0. So you could have done x squared, you could have done x cubed. I think doing the x cubed is definitely nicer, especially when you're looking at rational functions and you're looking and seeing, hopefully, that it just actually comes out to be a regular number. All right. So again, though, that is example 6 from our 1.5 number 2 set of notes.